Hi everyone, welcome to week 3 of hydrocarbons. We're going to begin with a starter today now that we've covered all of our homologous series. So I would like you to draw the following hydrocarbons. So if you pause here and give this a go, the answers will be up in a few seconds. Okay, here are your answers. If you mark them and give yourself a mark out of 6. If you're unsure about any of these answers, please just drop me an email and I'll give you a hand. Okay, so as with the last few weeks, this week's lessons will be split into 2 parts. The first part is quite small, it's called Properties and Uses of Hydrocarbons. So we're still learning about hydrocarbons. By the end of this part, you should be able to state uses for alkanes, alkenes and cycloalkanes. You'll be able to state the solubility of alkanes, alkenes and cycloalkanes. And you'll be able to describe and explain the trend in melting and boiling points of hydrocarbons as the number of carbon atoms in the molecule increases. So let's start with uses of hydrocarbons. So our alkanes can be used as fuels. Alkenes can be used to make alcohols and polymers, which are plastics. And cycloalkanes can be used as fuels and solvents. Now if we think about the solubility of hydrocarbons, alkanes, alkenes and cycloalkanes are all insoluble in water. Now you can either copy this out or you can print and stick out the handout that I've uploaded into the Microsoft Teams folder. Okay, now let's think about their melting and boiling points. Patterns are often seen in physical properties of members of a homologous series. So if we look here, we've got the alkanes, and this is taken from the data booklet. Now going from methane to octane, the molecule size is increasing. The number of carbons in the molecule is also increasing. And you can see from the melting and boiling points that these are also increasing. So what we can say is that as the size of the molecule increases, the melting and boiling point of the molecule also increases. Now let's have a wee think about why this is. So if you look here, we have got 3 molecules of ethane. Now, in between these molecules of ethane, there are small forces of attraction. These keep the molecules close together. Okay, so these forces of attraction hold the molecules together, but the forces of attraction are not the actual bonds within the molecule. So if you look here, between the carbon and the hydrogen, we have an actual bond within the molecule. The forces of attraction are between different molecules. Now, as the size of that molecule increases, the forces of attraction between the molecules get stronger. There are more of them and they're stronger. Now, when we melt or boil a substance, it's these forces of attraction that are broken, not the bonds in the molecule. So the stronger the forces of attraction are, the more energy is required to break them, and therefore the melting and boiling point increases. So let's just make sure we're happy with this. When we melt or boil something, it's not the bonds we are breaking, it is the forces of attraction between the molecules. And the stronger the forces of attraction are, the higher the melting or boiling point is going to be. So again, you can either pause here and copy this out, or you can print out and stick in the handout that's been uploaded into the Microsoft Teams files section. Okay, so like I said, that's quite a small section, and that's part 1 now complete. So we should all be able to state uses for alkanes, alkenes and cycloalkanes. State that the solubility of alkanes and alkenes and cycloalkanes is that they are insoluble in water. And describe and explain the trend in melting and boiling points of hydrocarbons. So that means that you describe that as they get bigger, the melting point and boiling point gets bigger, but explain that this is due to stronger forces of attraction between the molecules. Okay, on to part 2. So this is systematic naming of hydrocarbons is what we're learning about here. And by the end of this part, we should be able to identify the longest carbon chain in a hydrocarbon, identify and name branches on hydrocarbons, apply our knowledge of naming rules to correctly name branched hydrocarbons, and also apply our knowledge of naming rules to correctly draw branched hydrocarbons. So let's just remind ourselves of what we learned over the last couple of weeks. So alkanes have a general formula of CnH2n plus 2. Their names end in ane, and this tells us they've got single carbon-to-carbon bonds only. Alkenes have a general formula of CnH2n. Their names end in ene, and this tells us they contain at least one carbon-to-carbon double bond. And cycloalkanes have a general formula of CnH2n. Their names start with cyclo and end in ane, so this tells us that they've got single carbon-to-carbon bonds only, and they're formed in a ring structure. So let's now have a wee think about what systematic naming of hydrocarbons is. So far we've only ever looked at hydrocarbons where all the carbon atoms are connected in one long straight chain. But what if this isn't the case? So if we look here, these carbon atoms are not all connected in one long straight chain. But we still need to be able to name these hydrocarbons. So we're going to start off by looking at the rules and the steps that we would follow to name a hydrocarbon. Now this will be quite a lot of information given to you at once, but I'm going to give you all the notes first of all, and then we'll break it down and go through step by step what this means. So the first thing we do is we look for the longest carbon chain which contains the functional group. Now when we do this, this gives us the parent hydrocarbon name. The second thing we do is identify any branches if there are any. So if we can see a CH3 group, that is called a methyl group. Now remember, meth meant one carbon, so that's why it's CH3. If we have a C2H5 group, then it's an ethyl group. Now this might be drawn as CH2CH3. It might not be written C2H5, just for when you're looking for them. If we have C3H7, that is a propyl group. Again, this might be written CH2, CH2, CH3, if it's drawn out extended. Okay, so the second thing we do is identify any branches. Step 3 is to number the carbon atoms in the longest chain. Now we do this from the end closest to the functional group, and you'll remember doing this last week with our alkenes. Now if there is no functional group present, then you've got to number from the end closest to the branches, if there are any. Next we use a prefix to indicate how many of each branch we have. Okay, so for example, if we've got 2 methyl branches, then the prefix will be di. If we've got 3, the prefix will be tri, and 4, the prefix would be tetra. Okay. Number 5, we show the position of each branch, okay, and we do that by placing the number in front of its name. And then number 6, if there is more than one branch, we put them in alphabetical order. So for example, we would write the ethyl branch before the methyl branch. Now just a wee note, in between numbers we write commas, and in between numbers and letters we write a dash. Now this will make much more sense as we go through the rest of the lesson. So again, if we pause here and either copy this out, or we can print and stick the handout into our notes. Okay, so the first thing we're going to practice is identifying the longest carbon chain. So in order to do this, we need to look for the biggest number of carbons in the molecule that can be connected in one pathway. Now this will make a wee bit more sense as we go through examples. When we find this, this will tell us what the parent hydrocarbon is. So if we look at example 1 here, okay, in total in this molecule, there are 7 carbon atoms. However, they're not all connected in one pathway. You can't start at 1 carbon and follow and touch all 7 carbon atoms in one pathway. the longest chain we can see here is 5 carbons in a row. Now, because of this, and because there is no carbon-carbon double bond in that pathway, the parent hydrocarbon is pentane. So if we pause here and copy this down, now let's look at example 2. So again, in this molecule, there are a total of 7 carbon atoms. However, all 7 are not connected in one pathway. The longest carbon chain we can find is 6 carbons in a row. Now we can see there are 6 carbons in a row, and there is a double bond, and it's attached to the second carbon in the chain. So our parent hydrocarbon is hex 2-ene. Now a wee note here, the longest carbon chain must contain any functional group in the molecule. So in this case we had a carbon-to-carbon double bond that needed to be connected, or contained, in the longest carbon chain. So again, if we pause here and copy this down. And then example number 3. So in total here we have 8 carbon atoms. Now, when you look at this initially, it does not look like all 8 carbons are connected in one long chain. However, if we look at the highlight here, we can see that we can start at the carbon at the very left and follow one pathway all the way to the furthest along carbon at the end. Now, because of that, we can say that all 8 carbons are connected in a long carbon chain. Now, there are no double bonds, and so this parent hydrocarbon would be octane. So it's important to note that the longest carbon chain doesn't have to be in a straight line. It can bend and twist and turn as long as there's one connected pathway you can follow. So again, if we can just pause here and copy this example down. Okay, so we've got a couple of practice questions. For each of these, I would like you to identify and name the longest carbon chain and parent hydrocarbon. So if you pause here, there are the answers coming up in the next slide. So here are our answers. Number 1 is pentane, number 2 is heptane, number 3 is propene, and number 4 is hex 1-ene. Now I'll just show you here the highlighted longest carbon chains in each. And what we remind ourselves is that when we name alkenes with more than 4 carbons in the longest chain, you have to count from the side closest to the double bond. So if you look at number 4, the double bond is over at the right hand side, so we would start counting from that carbon in the right hand side. Okay, so the next thing we want to do is be able to identify any branches in the hydrocarbon. So what we can say is that any carbon atoms that are not in the longest chain can be considered branches, and they are named based on how many carbon atoms are contained in them. So if you remember back to when we looked at the steps, if we had a CH3, because there's 1 carbon atom contained in that branch, that was a methyl branch. So let's look at example 1 again. We've already identified our longest chain, okay, was in the middle, and that was our pentane. So we're now looking to see what remainder branches we have. So up the top here, coming off the main chain, we have a CH3, so that would be a methyl branch. And at the bottom, we have another CH3, so that would be another methyl branch. So again, we can pause and copy this down. Okay, on to example 2. So again, from before, we had identified our longest carbon chain. So we're looking for any leftover carbons as branches, and we can see here we have 1 CH3, which would be a methyl branch. Example number 3. Again, this is the same one from before. We have already identified our longest carbon chain. Now we can see here, all the carbon atoms are contained in the longest chain, and so this molecule does not have any branches at all. So if we just pause here and copy this example down. Okay, so a couple of practice questions again. I would like you to identify and name any branches in these hydrocarbons. Now these are the same ones that you have already worked out the longest chain for. So if you were unsure of any of them, use the longest chain given in the answers previous. So if we just pause here, the answers will be coming up in the next slide. So here are our answers. In question 1, we have a methyl branch, because it's CH3. In question 2, we have an ethyl branch, because in total on that branch there are 2 carbons. In question 3, we have a methyl branch. And in question 4, there are no branches at all. Now remember, the longest chain does not need to be in a straight line, as long as you can follow one pathway. So if we now go on and have a wee think about the actual systematic naming of hydrocarbons, bringing everything we've covered together so far to correctly name hydrocarbons using all of our steps. Now, what I would like you to do is have the 6 steps for naming hydrocarbons handy for you to refer to when we go through examples together. So that was the slide that covered 1 to 6, showing you talking about finding the longest chain, identifying branches, numbering the hydrocarbons, etc. Have that with you as we go through these examples. So example number 1. The very first thing we do is identify our longest chain. So we've done this already, and so we know the parent hydrocarbon is pentane. The next thing we do is identify any branches. So we already know there's a methyl branch up the top and a methyl branch at the bottom. Now step 3 is to number our carbon chain. Now we would usually do this from the end closest to a functional group. We don't have any functional group here, so instead we number from the end closest to the branches. Now because the branches are right in the middle of the molecule, we can number from either side, it does not matter. So we number our carbon atoms 1, 2, 3, 4, 5. Then we're going to look and see if we have any prefixes to use based on the number of branches. So we can see we have 2 methyl branches, so we write that as dimethyl. Our next step is to identify what number carbon the branches are attached to. So we can see that both branches are attached to carbon number 3. So we bring this all together to name our hydrocarbon, and we call it 3,3-dimethyl pentane. So what this tells us is that on carbon number 3, there is 2 methyl branches attached. Now remember, we place commas in between numbers in the name and dashes in between numbers and letters. So if we pause here and copy this down. Okay, on to example number 2. So again, our first step is to identify the longest carbon chain, making sure any functional groups are included. So we do this by picking the 6 carbons in a long chain, and so our parent hydrocarbon is hex 2-ene. Remember, it's hex 2-ene because the double bond starts on carbon number 2. Then we identify that we have a methyl branch. Our next step is to number our carbon chain, and we do this from the end closest to the functional group. So we start from the left hand side. 1, 2, 3, 4, 5, 6. Now there is only 1 methyl branch, so that will just be called methyl. We don't need to use any prefixes. We can see that the methyl branch is attached to carbon number 2. And so we put this all together to give our name, which would be 2-methyl hex 2-ene. And this tells us that there's a methyl branch on the second carbon of a hex 2-ene molecule. So again, if we just pause here and copy this down. Okay, example number 3. We've already identified the longest chain in this example, and we've decided that the parent hydrocarbon is octane. We can see that there are no branches at all, and so we don't need to do anything other than name this molecule octane. Because there are no branches, there are no functional groups, we don't need to worry about numbering the carbon chain in this example. So if we copy down that final example of systematic naming. Okay, so we have 5 example questions now to systematically name. Now 1 to 4 are the ones that we have already covered in terms of practicing our longest chain and identifying our branches. So if you need to refer back to the previous answers, please do that. Number 5 is one for you to try completely on your own. So for number 5, you'll have to identify the longest chain yourself, identify and name any branches yourself, and then do the remainder steps as well. So if you pause here, try the questions, the answers will be coming up in just a little minute. Okay, so here are our answers first. I'm going to show you the answers first of all for you to mark, and then in a second I'll show you the working that we would use to work them all out. So number 1 was 3-methylpentane, 2, 3-ethylheptane, 3 is 2-methylpropene, 4 is hex-1ene, and 5 is 2,3-dimethylbutane. So let me just show you the working now. So for each of them I've highlighted the longest chain, I've circled any branches, and I have numbered the chain. Now if you're still unsure of any of these at all, and you're not quite sure how you got your answer, or why it doesn't match up, please email me. Send me a picture of your working, and we can work through together to figure out what steps you might have done wrong. Okay? So now that we're happy naming a hydrocarbon from the full structural formula, we're going to go the opposite way. So what we now want to be able to do is use the systematic name to draw the full structural formula of a hydrocarbon. Now to do this, we follow similar steps as we did when we named hydrocarbons. So these are the steps we'll follow. The first thing we do is draw the carbon chain of the parent hydrocarbon. We don't draw the parent hydrocarbon in full, we just draw the carbon chain first. The next step we do is we number the carbon chain. Then we draw any branches on the appropriate carbon atoms, and then we fill in our remainder hydrogen atoms. So let's look at an example. We're asked to draw the full structural formula of 3-ethyloctane. So our first step is to draw the carbon chain of the parent hydrocarbon. In this case, our parent hydrocarbon is octane. Now we remember that oct tells us there are 8 carbon atoms, and the ane tells us that they're only carbon single bonds. Number 2 is we number the carbon chain. Now because we are drawing it, it doesn't matter what side we number from. So I've just numbered from the left, 1 to 8. Step 3 is to draw any branches on the appropriate carbon atom. Now the name of the molecule is 3-ethyloctane. This tells us that on carbon number 3 there is an ethyl branch. And remember, eth tells us there's 2 carbons, and our ethyl branch would be C2H5 in total. And then step 4, we fill in the remainder hydrogen atoms. Now to do this, you look at every carbon in turn and how many bonds are currently attached to it, and you make that up to 4 by adding hydrogen atoms. So for example, on carbon number 1, with no hydrogen atoms, there was only 1 bond, so we needed to add 3 hydrogen atoms to make that up to 4 bonds. So if we pause here and copy this example down. let's do another example. This time we're asked to draw the full structural formula of 2,4-dimethyl-pent-2-ene. So our first step is to draw our carbon chain of our parent hydrocarbon, and that is pent-2-ene. So pent tells us there are 5 carbon atoms, ene tells us there's a carbon-to-carbon double bond, and the 2 tells us that it's on the second carbon. So we now number our carbon chain, and we need to number it so that the double bond starts on carbon number 2. Step 3 is to draw any branches. Now, our name says 2,4-dimethyl. Dimethyl tells us there are 2 methyl branches. The 2,4 tells us that one of those methyl branches is on carbon 2, and one of those methyl branches is on carbon 4. So if we look here, we now add our methyl branches on. So carbon 2 has a methyl branch, carbon 4 has a methyl branch, and our last step is to fill in the remainder carbons with hydrogens. So again, you look at every carbon in the chain in turn, count how many bonds are currently attached, and add hydrogens to make that up to 4 bonds. And when we do that, we should end up with this molecule here. So again, if we pause here and copy this example down. Okay, now we're going to have a wee look in depth at shortened structural formula. Based on last week's exercise, I can see that a few people are struggling with shortened structural formula a little bit. So we're going to look at this a wee bit closer in detail just to make sure everybody's happy. Now, when it comes to representing branches in shortened structural formula, we write them in brackets. Okay, so let's look at a wee example here. So if we start with this molecule, remember when we write shortened structural formula, we look at every carbon in the chain in turn and collapse the carbon-hydrogen bonds and collect them all together. So if we look at this first carbon here, we can see that it's a carbon with 3 hydrogens attached, so we write CH3. Our next carbon has 2 hydrogens attached, so we write CH2. Our next carbon here has 1 hydrogen attached, and then also connected it has a branch. Now that is a CH3 branch, and so we write that in brackets. So when we see anything in brackets, that tells us it's a branch attached to the carbon before. Then our next carbon is CH2. We have another CH2, another CH2, and then lastly our CH3. So this would be the shortened structural formula for that molecule there. Okay, so if we copy that example down. Now if you're still unsure about how shortened structural formula work, just give me an email and I'll give you a hand, okay? Okay, now in the same way that we want to be able to write the shortened structural formula from a full structural formula, we want to be able to use a shortened structural formula to write the name of a hydrocarbon. So let's look at an example. I want you to name the hydrocarbon represented by the shortened structural formula here. So let's look at how we would do this. Again, we would look at every carbon in turn in the same way. So we start off with a CH2. Then our next carbon is CH. Our next carbon has attached a H and also a CH3 branch. Now remember, it's in brackets, that's how we know it's a branch. And then lastly, we have another CH3. Now the last step is to connect the chain together. Now what we do is we look at every carbon in turn, starting at the first one, count how many hydrogens are attached, and how many bonds should be remaining. So at the very first carbon, there are currently 2 hydrogens attached. We know carbons make 4 bonds, so to make that up to 4 bonds, there must be a double bond between that and the next carbon. We can now see the next carbon has a double bond attached to and a hydrogen, so in total has 3 bonds. So there must be a single bond between that and the next carbon. And then on our third carbon, there's currently 3 bonds attached. So it must only be a single bond between that and the next carbon. And then we can see that the last carbon now has 4 bonds attached. And so that is the molecule complete. Now that we have the entire molecule drawn out as a full structure, we can use our naming rules to name this molecule. Okay, so what we do is identify the longest chain, look for any branches, number the carbon atoms, and then follow the remainder rules. And if we do that, we should get 3-methyl-but-1-ene. Okay, so what I would quite like you to do is have a wee look at this molecule, go through the naming process yourself and see if it matches up. If it doesn't, let me know and we can figure out why. Okay, so if we just copy that example down. Okay, so that's now part 2 of the lesson complete. Okay, so we were learning about systematic naming of hydrocarbons. We should now all be able to identify the longest carbon chain, all be able to identify and name branches on hydrocarbons, and then apply our knowledge of naming rules to correctly name branched hydrocarbons and correctly draw branched hydrocarbons. So this week we have exercise 3. This covers our properties and uses of alkanes, alkenes, cycloalkanes, and also our systematic naming. So what I would like you to do is pause and complete these questions and submit your answers to me. Now, as always, you can either do this through Microsoft Teams, through email, or on your class notebook. Okay, this is out of 15 marks and it is due on Monday. Okay, if you've got any questions, you're unsure of anything, please email me. I'm always here to help. Okay, good luck.